we're going to be talking about computational sidechain packing. So first off, what is the packing problem? What do we mean by packing? And it's given a protein backbone, coordinates, and the sequence. We're going to determine the coordinates of all of the sidechain atoms. This is big enough for everyone to read, right? Great. So why would we endeavor to do this? We're going to need the sidechain coordinates to create complete 3D models of protein. And you can imagine if we had two proteins that were crystallized and we had their sidechain coordinates in perfect resolution. If we wanted to simulate docking or something, those sidechains might move around. So we need to simulate that flexibility for other applications. So, flexibility for docking, design, etc. And so docking and design are topics that will be covered later on. So, as always, we need sampling and scoring. So sampling is going to create conformations, and typically that's going to be done by sampling chi angles. And for scoring, we need to rank the alternate conformations. And then we need to pick the best one needed to model. So what's the scale of this problem? About how difficult is it? So let's start off with a 50 amino acid residue protein, so that's pretty small. And let's say that there's an average of 2 chi angles for every residue. And let's say we were to sample every 40 degrees of each of these things. So we're doing kind of a continuous sampling of all these degrees of freedom. And so what this ends up meaning is that for every chi, which can be 360 degrees, full circle, we sample every 40 degrees, raised to the 50th for the number of residues we have, times 2, take the number of chi's we have. So this ends up being about 10 to the 95 conformations that we would need to sample through to do an exhaustive sampling of a really small peptide. So this is too large. So that's the problem. But let's go back to these chi angles, when we talk about how many they have, and do some structures real quick. So we're going to talk about the side chain, torsional degrees of freedom. And we'll start pretty small, talk about veiling. Everyone knows the structure of veiling, right? That's been a little quiz that everyone's had, right? So we just draw a simplified representation of this. Gamma 2. This bond angle right here, the angle around that is pi 1. And so as you were to rotate this bond, these C gammas out here are going to be rotating around the plane of the board. That's going to be that. And so this side chain has 1 degree of torsional freedom. So we have 1 chi. And other side chains with just 1 chi are serine, threonine, cysteine, and bromine. So another one is serine, and I'm going to draw that one too because it's a little easier to see because we have only the 1 branch off of the carbon. So I'll draw that down here. So we can also take a look at leucine, which has 2 chi angles. There's chi 1 and chi 2. And so other amino acids that have 2 chi's are aspartic acid, asparagine, isoleucine, tryptophan, tyrosine, phenylalanine. 3 chi's, M, E, and Q. 4 lysine, 5 is arginine. Okay. And so these angles are always going to be defined using the atoms of highest priority. So for example, over here is C gamma 1 and C gamma 2. C gamma 1 is a higher priority, and so that is the atom that's used to define the chi. And let's start off with a human projection. Everyone remember these from organic chemistry? They're terrible. Okay, so if we have this type of conformation where nothing's eclipsed, where do we put the OH? That's the question we have for building up serine. There are 3 possibilities. Okay, So we can stick the OH here, here, or here. So draw all of these out. And when it's here, you'd have to rotate, if you're looking down the C beta C alpha, so alpha is behind beta in the plane of the board, or normal to the board. You'd have to rotate this top piece about minus 60 degrees to superimpose the OH on top of the nitrogen. So that's the value of chi1 here. In this view, it's the how much you have to rotate the OH to superimpose on top of the N. And so if the OH were here, it would be 60 degrees. If the OH were here, it's 180 degrees. And so these possibilities that are more or less discrete are called Rotamers. They're distinct conformations that the side chain can adopt, and they have nice little names. So when chi1 is about minus 60 degrees, which could also be 300, we call that gauche minus. That can be abbreviated G minus, just the minus sign, the letter M. When it's plus 60, call that gauche plus. That's abbreviated G plus, plus sign, letter P, and it's about 180 degrees. We call that trans, and that's abbreviated the letter T. And so if we look more at these distinct conformations, we can look at known structures and compute some statistics on how frequently we observe each of those conformations. And so as a rough sketch, let's say 30, 60. Well, we're not going to get the full 300. We can see around 60 degrees it would be a little peak. Around 180 it might be a shorter but broader peak. And all the way out here we see a peak that might be more or less symmetric to this one. And so each of these conformations aren't equally probable. And so I guess the first question we have is, why is that? Does anyone have any ideas why that might be?
The repulsions between two groups would cause an energy, unfavorable energy.
Right, so the basic idea being that this side chain isn't by itself, right? There's the whole rest of the protein around it. There's other context that needs to be considered. There's the rest of the side chain. There's a backbone. There's other residues that it's bound to, etc. And so all those things are going to contribute to those distributions. Okay, so let's look at an example. This comes from Learning Car Plus in 1979. And it's an MD simulation. And this should be listed as part of the recommended rating, so you should be able to find it pretty easily. So if we look at Okay, so this is chi1, 0 to 360, chi2, 0 to 360, and this is Y35 of the trypsin inhibitor. Turns out that we see two distinct populations come out of this simulation. Something right here. There's another one. And so for this population, we have a chi1 of about 175 degrees, chi2 about 200 degrees, 160. So this lower one, chi1, 175, chi2, 60. Okay, so the important thing here is that discrete sidechain conformations correspond to local minima and potential energy using molecular mechanics force fields. Okay, so I'll write that. Okay. So let's go back to what would determine this distribution. We briefly touched on over here. So everyone remembers from organic chemistry that the staggered conformations are going to be preferred to the eclipsed conformations. And the thing that might not be quite as obvious is that the preferences for exactly what is preferred is going to depend on the backbone conformation. Okay, so to see why, let's draw another Newton projection. Okay, so phi is the rotation around this bond, psi is the rotation around this bond, and some codes. So chi1 is trans, that's this guy is the highest priority. And phi is 0 degrees, 180 degrees. So you can see what's going to happen here is that this is going to be rotated. This will completely opposite, and these guys are going to clash with this, right? So in that case, the trans distribution is going to be a little suppressed. It's not going to be as energetically favorable. Likewise, So if we're in the gauche minus, we can also clash with the backbone if the phi is 0 or 180. And there's another dependence on phi, which is that if this nitrogen is involved in a hydrogen bond, we'll call this OHB and CHB, it can actually clash with the gauche plus rotamer. When phi is minus 120 degrees or 60 degrees. Okay, so that's a little bit about the backbone dependence of particular rotamers. And being able to solve all this stuff outright would be a lot of work and probably pretty error prone because we would miss a few things that matter. So instead what we do is we study a lot of solved crystal structures and we calculate Rotamer libraries based on them. So Rotamer libraries are record the conformation of the various side chains. The Rotamer libraries are sets of discrete chi combinations that are going to define a limited but energetically complete set of sidechain conformations. So it's going to be a much smaller space than that every 40 degrees sampling, but it should have everything in it that is energetically favorable. Okay, so there are two leading libraries, and when we say leading, we also mean recommended. So I'll put that back. The first is called the penultimate. Rotamer library. From Lovell and Richardson. The second one are Dumbrack, Cohen's backbone independent, backbone dependent. And so both of these have had updates to them in the years since they were initially published, but people will still typically refer to them by these names. Okay, so we have a couple of slides just to kind of talk about what rotamers are, what the libraries format are, and to give you a sense of the kind of information that we're recording there. So you can see here there are 4 phenylalanine rotamers. The chi1 is a rotation around this bond. You see the different conformations there. They're discrete sets. And we compare that to arginine. There are 34 rotamers. You can see there's a lot more space that would need to be sampled here to get an accurate representation. So 434. Okay. So first, this is Dumbrack and Cohen's backbone independent rotamer library. And so in this column we have the amino acid. This is the chi 1, 2, 3, 4. And then this is which version of chi it is. And you can see the value corresponding over here. So this is the gauche plus, trans, gauche minus. And it tells you the probability of being either of any of those. And if we look at the backbone dependent version, there's these 2 extra terms for phi and psi. And you can see that there's every rotamer for a given side chain is being enumerated at each conformation, and I believe this has been in a 10 by 10 grid. So now you have an explicit probability stated for every backbone conformation. And so this is are some of the data from the penultimate Rotamer library. And so instead of using chi-bin 1, 2, or 3, they use the abbreviations P for ghost plus and for minus and T for trans. So for isoleucine, there's 2 chi's. So we have PP is plus plus, plus trans, etc. And instead of being broken down for every explicit 10 by 10 grid, it's split up into alpha, beta, and other. And so this other bin is quite large, you might imagine. And then the percentages, the distributions are reweighted within each bin. So that's how all of these can still add up to be about 100%. And so here's a larger set of all of these rotamers. You can see that for arginine, again, we have a lot of different values. So this is PTP 85. And so what that means is that last chi value doesn't quite fit into one of those bins, so they've explicitly given the mode of that last bin. You can see that a lot of these have sort of numbers tacked on the end there. And so you can see how these numbers are all going to get read in, they're going to be used for sampling software. So, what are the advantages of Rotamer libraries? Why do we use them? Rotamer libraries significantly reduce the search space, even in the case of arginine. And for some comparison here, even small libraries with 100 to 150 rotamers in them, they cover about 96% of the protein conformations that we do. The probable conformations, I should say. Okay, so we can use those probabilities that are stored in the libraries to estimate energies. I'm sure you've seen this equation a bunch of times now, but it's important. And so, in each of these cases, what this P is going to be a little bit different. So there's probability is a function of the given value of chi given the secondary struct. Right, so whether it's alpha, beta, or other, it's going to change the probability of a particular bin you're in. And so this would correspond to the penultimate. And then there's the Dumbrack backbone dependent library, which would be the probability of a given set of chi's given phi inside the backbone. Okay, so that's how we can take those probabilities out of the libraries, and put them into a score function. Okay, so where does this get us? So if you remember, we previously estimated that a small protein, 50 residues, an average of 2 chi's per res meant that there were about 10 to 95 conformations. So now, there's 2 chi's. Each chi has about 3 rotamers, right? Typically, we're just going to see that goes plus minus trends. 3 to the 2, 9. So there's 9 rotamers per residue. And there's 50 residues. So now we have 9 to the 50, which is about 10 to the 47 conformations. So this is much, much better than 10 to the 95. It's still too large. Better.
Can you explain again why is there 9 rotamers per residue?
Oh, sure. So for each chi, there's 3 possibilities. So 3 to the 2 is 9. Does that make sense? Because they're totally independent. So the question we have now is, how do we search discrete libraries for total protein conformation? Okay, so the idea here is we want to find from these libraries the conformation of a particular protein. And so there's several methods. I'm just going to list a couple of them out, and then we'll go into detail about one of them. The first is called a greed search. It's pretty naive. It's really going to be useful just for small proteins. It doesn't use rotamers. It just samples at a fixed resolution for each thing. So only small proteins. The next is called dead-end elimination. And that's usually abbreviated DEE. We'll talk about this one in a lot of detail in a little bit, so just hang tight. There are self-consistent algorithms. These are going to have a really variable runtime. Only a small amount of space ends up being sampled in these because it's sort of, it's an iterative approach to doing this, and it's often hard to find the global minimum with these types of approaches. So, let's see. Small sampling. Hard to find global minimum. And then there are Monte Carlo approaches. And so those are going to involve selecting residues at random to try new rotamers and that sort of thing. And in particular, there's an approach implemented in Rosetta that uses a triad. I'm so going to list that one explicitly. And so the idea here is this is a special kind of data structure. It's a tree. And it can reuse atoms that are common in different sidechain types so that you can speed up the energetic calculation. So it uses common atoms. As you might imagine, sampling and scoring are sort of linked to each other. So if we can rank more conformations in the same amount of time, that's going to help us sample more. And as I said, like DE. Okay, so it's been around for a while. It was published in Nature in 1992 by, I don't know if this guy is French or not, but it would be Desmet et al. And the basic idea is we want to eliminate bad rotamers. So if we can identify a particular rotamer as being incompatible with a global energy minimum, we can eliminate it. We don't have to sample it anymore. Okay, so I'm going to eliminate bad rotamers. What that's going to let us do is narrow the search space. You got to be careful, because if you can inadvertently remove a good rotamer, it's out. You can never get it back. So. Okay, so we want to be careful not to remove rotamers that are part of, and this is what they refer to the native conformation is the global minimum energy conformation. That's abbreviated GMEC. Okay, so as always, we want to use an energetic calculation or estimate to decide which rotamers are bad. So here's their energy function. There's three terms. There's the energy of the template. Which are the backbone terms. So this is also called the template self-energy. There's the energy of a particular rotamer at position I. And so that's it's a one-body energy. But it might include some interactions with the template. So it's not entirely one body. It's just one body in terms of how it interacts with side chains. And then there's this two-body term of rotamer IR with rotamer JS. Okay, so that's how any two rotamers are interacting with each other. So that's two-body energy of IR with JS. Okay. Everyone's agreed, right? So, using those three terms, we're going to say that our global energy is the sum of the template energy popping on the next line, but this is a plus. Sum over all positions I of EVIR plus the double sum of I, R, and J, S interacting with each other. So the total energy is the sum of all of these sums for every position in the entire protein. So the idea is that if we can find a particular IR who has an energy that, minimum energy, the best case scenario with the rest of the protein, is worse than some other rotamer in that same position, we can throw that rotamer out. Okay? So I'll write that down in math, and I'll draw a picture, a plot, and then we'll look at some examples. Okay. Min. Okay, so again, what we have here is if the minimum score of IR with all other combinations is higher than the maximum score of any other rotamer at the same position, IT. And we know that IR is not compatible with the GMAC. So we can safely eliminate IR from the set of rotamers that we're going to be considering at that position. That make sense? All right, so equations. Everyone loves equations. Pictures are a little bit better for some people, though. So let's turn this into a quick picture. So if we have rotamer space here, that's basically what JS is, the rest of the context. We have score on the vertical axis. And then this is the score as we move through rotamer space of rotamer IR. And so the minimum is right there. Okay. But now if we have some other rotamer at the same position, IT, and it's like this, and its maximum is there, let's say. You can see that this maximum is lower than this minimum at all, globally and at all points. So that means that this IR cannot be part of that of the low energy confirmation. So there can be more complex criteria you could use. An example of that is the Goldstein criterion. which basically means that you could see that without even this being globally true, if it were just locally true, that would be sufficient to be able to eliminate IR. And that's what the Goldstein criterion is, a formulation of that idea. Here's what it looks like. Okay, so in case you can't read it, it's sort of in the corner. This is E of IR minus E of IT plus the sum of the minimum of the difference of E IRJS minus EITJS. And so what this allows us to do is to have a situation like this. You can see here that this maximum is higher than this minimum. And by this criterion, we would have to keep I bar in the set. But what we can see here is that every single point, the rest of the context of that protein, IT is superior, so we can still throw out. Okay, so you can also expand these, re-express these criteria in terms of pairs of residues, larger segments. They can become really complicated, so we're not going to do that. So, all right, so this is figure 1 from Desmond's 1992 paper, and on the left-hand side are the buried side chains, and on the right-hand side are the solvent-exposed side chains. And so in bold, what we're seeing are the deviations from. In bold, what we're seeing are their predictions, and you can see the deviation from the crystal structures, which are these finer colors. And so you can see that for the most part, these are very, very close. In fact, the RMSD is about 0.6 angstroms over all of these bolded side chains. Over here, these are all the exposed ones. The RMSD is a little bit higher. It's 1.9. And that kind of makes sense because you might imagine that, again, in a crystal structure, we've talked about this before, that there are other proteins around it. It's not the same as if it were just solvent exposed. There might be more allowable conformations than are actually realized in the crystal environment. Okay. And so here's an example of where N here is the number of rotamers they have to consider. And so they start off, this protein has 76 residues that they're going to be considering. And there's two types of simulations here. The one with circles, where they alleviate clashes first. And they say, they determine which rotamers can't go because they'll hit the backbone or something like that. And I believe they also use which pairs can't go together. And then the triangle points are where they did not remove those rotamers up front. And you can see they start off with almost 10 to the 80 rotamers they need to consider. Right, so that makes a lot of sense of what we said. There's about 2 Chis per residue, so it's about 9 rotamers, 76 positions. So that all makes sense. So A, B, and C are these clash rules, and then D1, 2, 3 are just rounds at that elimination that they're running. And so each step, they place every rotamer in every position, and they throw out the bad ones. And then they also look at which pairs can't go together, and they just record those for the next iteration, and so they don't have to try those pairs anymore, so they know that they don't go together. Okay, and so the interesting thing here is that in just a few rounds, they're down below 10 to the 10, which is 10 billion, and is still a huge number, but is certainly much more tractable than that 10 to the 47 that we were working with before. Yeah, so then within 9 rounds, they went from about 3 times 10 to the 76 to 7,200 as their value for n. It's a number of rotamers that you consider. So 7,200 is certainly a tractable number. And let's go back over here. Okay, so let's see. So they started off, we'll call that n naught, with 2.7 times 10 to the 76 rotamers. After 9 rounds, they had 7,200. And 55 of the 76 residues had correct rotamers, or at least agreed with the crystal structure. And so when they say correct, what they mean is that each chi is within 10 degrees of what it is in the crystal. It's pretty close. And if we only consider the buried residues, we're at 93%. Correct. And so overall, 72%. Okay, so now we have a couple of questions for you guys. Why is it that when we do something like that in elimination, we require the backbone to be fixed? So we talked about this whole time where we have this template, it's totally static, can't move at all. Why might that be important?
I think so. Once you eliminate something, right, if you try to twist the backbone, you might change the energy, so then maybe what you eliminated would no longer be, be higher. So then we wouldn't want to do that.
Right, so in this particular algorithm, it's pretty important that once something's out, it stays out. So any other reasons we might want to do that?
We're already trying to reduce the search space, which is a big, if you allow backbone movements throughout this, that just makes the search space a lot bigger.
Yeah, exactly. All right, so what would be the difference then between what a protein might be doing in nature and when we run a packing simulation like this? Protein backbone's static in solution. No, they're flopping around a little bit, right? So small errors in backbone coordinates could lead to pretty significant problems. So especially in data elimination, backbone resolution is very, very important to getting a reasonable result. So Monte Carlo, Rotamer packing very briefly. So in a Monte Carlo algorithm, we're going to randomly choose a position and a rotamer and try it out. Then we're going to evaluate the metropolis criterion. And in case we forget, that's that the probability of acceptance is e to the negative delta E over KT. And the force field that we use is going to contain those EI and EIJ terms that we were using explicitly over here. So that's the one body and the two body terms for the Rotamers. And we can use simulated annealing to avoid kinetic traps. Have you guys talked about simulated annealing before? Okay. Okay, so if we're using a Monte Carlo method, do you think that finding the GMEC, that's the global minimum energy conformation, is guaranteed anymore? Shaking your head no. Why not?
Because you're changing the global configuration when you simulate an anneal, for example.
So I mean, is it guaranteed that you're hitting every residue?
No.
So is it guaranteed that each position? So in that elimination, you're going through every position, you're trying every rotamer. We're not doing that anymore. Now we're picking things randomly and trying random rotamers. And so there's no longer a guarantee that we're actually going to even sample what would be the global minimum. All right, so this is a video of hacking top 7. Jens Meiler made it. He's at Vanderbilt and graciously allowed us to use it. You'll hear all about top 7. I'm talking about design. Okay, so first what we're seeing here, these are the crystallographic positions of the side chains. And now this is Rosetta sampling different rotamers using the backbone-dependent Rotamer library from Dumbrack. And you can see that the identities of the side chains are fixed, but there's all the rotatable bonds are being sampled in one row. And then so it finds a nice conformation that it likes, and you can see how close it ends up being to the crystallographic coordinates. So when we see a snapshot of side chains, if they're really well resolved, it could just be that they're interacting with a crystallographic partner, or there's like an ordered solvent in the crystal, and in solution that solvent might be moving around a lot more, and so that might not be a fixed position. But in the core, those positions should, if they're not fixed, should stick around for a lot longer. And so these issues really come out when you want to go and get more detailed information from the crystal structure. So let's see. We've got detailed issues. So I mentioned the tri-E earlier, where you can use common atoms to speed up the calculation. And so that's nice for us. But sometimes there are these non-canonical positions. And these are going to be explicitly stated at level. So you remember when we showed that arginine in the table, there was all those numbers after it. It was the 85, where it wasn't exactly where you might expect it to be. That's what we're talking about, these non-canonical positions. And so getting the more detail requires going off rotamer, if you will. Yeah. And in the same library, they provide what are called single sample points for exceptionally broad wells. So sometimes your peak is a little broader than you might want it to be, and if you were just sampling the middle of that, you're not going to actually recover what the native distribution actually looks like. So there's single sample points. And so those kind of look like S, PT, minus 60, and this is P. And so, let's see, E, Q, F, and Y all have single sample points listed out in the Rotamer library. There is some discussion about how much backbone dependence there really is in different Rotamers. In the Dunbrack library, every 10 by 10 grid is listed out. Explicitly. In Lovell, the penultimate library, we just had those three categories, alpha, beta, other, except for aspartic acid and asparagine. So they say these actually do have backbone dependence. And what that means in this context is just that the peak of that distribution is moving, not just the frequency of observing them. So it's actually a different distribution. I have a video in just a second to show what that looks like. And then perhaps most egregious issues that come back to crystal structures is the case where there are alternate conformations. And so you can imagine if there's two Rotamers, let's say they're equally probable, and you're diffracting a whole bunch of copies of a protein, about half are going to be in one conformation, and half are going to be in the other. So you might see density that looks something like, you can imagine. So you can imagine if there's an alternate conformation here or here, so half are here and half are here, that it would be not the right thing to do to stick it here. And that's exactly what has happened in a lot of, or not a lot of, in some crystal structures. And so that's wrong. And so another view of this, if you guys make this, you had half in this conformation, half in this conformation, and the coordinates that were submitted like this. So this is going to throw off Rotamer libraries. It's wrong. Let me show you a quick video, because we're almost out of time. What we're showing here is chi2 versus, this is the probability given phi and psi. And in time, we're scanning along psi, and we're moving along in phi when we get to the end there. So you can see that it's not just that this distribution is changing its height or width, it's actually changing where the peak is. And so that's an example of backbone dependence. It's not just the frequency of the Rotamer, it's what the Rotamer actually is. I think that's any questions?
So do we have backbone dependence? What, like when would we use the independent backbone?
So the question is, when would you use the backbone independent library? For simpler calculations, you could imagine if you were trying to, for statistical purposes, you might be trying to get like a background frequency. If you needed to do something more exhaustive, if you're trying to design a protein and you want to figure out what amino acid you should put at a particular place, you may also be allowing the backbone to move. And in that case, you may want to have the backbone independent.
So it's less data and less calculation?
Yeah, it's less data because there's none of this. There's not, instead of like a bin for each phi and psi, there's just a bin.